Hello everyone, we want to do this problem, and this is a system of piston and cylinder. We have 5 kg of saturated vapor liquid mixture of water, and initially at 100 kilopascal. Out of this 5 kg, 2 kilograms is in liquid phase, the rest is in vapor phase, and then we apply heat to the system. The piston starts moving upward when the pressure inside the cylinder reaches to 125 kilopascal. We want to calculate a couple of properties here. The heat is applied until the total volume is tripled. Alright, so in order to calculate this, we need to write some of this information here. So we have 5 kilograms of water, right? And initial pressure is 100 kilopascal. Then the mass of liquid, which I just name it F, right? Or liquid, it's 2 kilograms. Mass of gas is 3 kilograms. And I should write F1, mg1, because that's at the state 1, right? Now at state 2, pressure is 125 kilopascal. And the volume at this state would be variable. So the heat is transferred until the volume triples, right? So the volume 3, basically we have 3 states, right? I'm going to draw it for you, but let me write this. So initial state, you have a piston cylinder device, right? And there are a couple of stops here. Right, and then the piston is on the top of this. That's initial state, right? And in this state, the pressure inside is 100 kilopascal, right? And then we have heat applied to this system. So let me call this Q, and that's from state 1 to state 2. What happens at the state 2 is you are still at the same volume because your piston does not really move until your pressure inside reaches to 125 kilopascal. That's where the piston starts moving upward. This is state 2. The volume has not changed. And then you continue applying heat to your system until you reach another state. And that state is state 3, and not the best picture. Let me redraw it. The scales are not correct, but let's assume that this volume is triple than that volume, right? So this is a state 3, and the volume has tripled, so volume 3 is 3 volume 2. And what is the pressure? Pressure is still 125 kilopascal if we assume that we have a frictionless piston, right? Cool. All right, so what we want to do the first is the mass of the liquid water when the piston first starts moving. So now before doing that, we need to calculate the specific volume. So pressure 1, state 1, basically. P1 is 100 kilopascal. It's of course a saturated vapor liquid mixture. If you refer to the tables at P saturation equal to 100 kilopascal, that's table A5, you can read the values of nu F, which is 0.001043, and you can read the value of nu G, which is equal to 1.6941 cubic meter per kilogram, right? Now, we are somewhere between these two specific volume because it's a saturated vapor liquid mixture. We can calculate the quality, is the mass of the vapor or gas divided by total mass, and that is 3/5, which is equal to 0.6, right? That was given to us, and based on that we can calculate the specific volume at state 1. So specific volume is equal to 0.001043 plus 0.6, which is x, multiplied by nu fg, which is the difference between these two specific volumes, 6941 minus 0.001043. You do this calculation, you get 1.017 cubic meter per kilogram, right? So that's the specific volume at state 1. What is the specific volume at state 2? Well, it's the same, right? Because your volume has not changed, the mass has not changed. So specific volume 2 is equal to, this is 2, 1, and that is equal to the same number, 1.017 cubic meter per kilogram. And also, you know that your pressure at this point, at the state 2, is equal to 125 kilopascal, right? Okay, so we have this information, right? And you need to know what is the state of your system at state 2. Okay, in terms of, are you in compressed liquid, are you in superheated vapor, or you're still in saturated vapor liquid mixture, right? So what you need to do in order to understand that is to go at that pressure at P saturation equal to 125 kilopascal and read the values of nu F and nu G and check to see if your specific volume would be between these two values, or it's more than, or it's less than. Okay, so by checking that, you will see that your value of nu 2 is less than nu G. This is again at 125 kilopascal, and more than nu F, which means that you are still in saturated vapor liquid mixture. Okay, so we have this, right? And that would be the state of our system at that point, right? And now, what is the quality? Again, we can use the same equation we used here, but this time we solve for quality. So nu 2 is equal to nu F plus x2 multiplied by nu G minus nu F, right? And you can solve it for x2, and that would be equal to 1.017 minus 0.001048. These numbers are at 125 kilopascal from table A5. So if you solve this, you get 0.74, almost 0.739. Okay, so that's your quality at state 2, right? So at state 2, the mass of the gas therefore is equal to your quality, which is 0.74 multiplied by 5, right? That would be the mass of the gas, which is 3.697, and you can calculate the mass of liquid, which is the difference between the mass of gas and total mass. That's 1.303 kilograms, right? So that was this part, which the mass of the liquid when the piston first starts to move. That's state 2, right? Now we need to calculate the work done during this process and also show the process on a P nu diagram. So in order to do that, we need to, because the piston moves, it's a boundary work, right? So the boundary work, you can use the first law of thermodynamics, but you need to have some information about the state 3, right? So state 3, remember the volume 3 was equal to 3 volume 2, right? And since there is no mass leaving your system, this means that your specific volume is equal also to 3 nu 2, right? So you can calculate the specific volume at that state, which is 3 multiplied by 1.017, that's 3.051 cubic meter per kilogram. And since it's a frictionless piston, your pressure stays the same, 125 kilopascal. Now at 125 kilopascal, you compare your system, and you will see that nu G at that pressure from the saturated, that's table A5. Nu G at 125 kilopascal is equal to 1.375 cubic meter per kilogram. You compare these two numbers, you see that this number is much higher than that, therefore you are in superheated region, right? So nu 3 is more than nu G at 125, therefore superheated vapor state. And your pressure is how much? Is 125 kilopascal, right? So in order to calculate the work done during this process, you can just simply say work is pressure multiplied by volume 3 minus volume 2. Pressure stays the same, right? 125 kilopascal, and the total mass does not change. That's 5 kilograms, and multiplied by the difference between specific volumes, right? So 3.051 minus 1.017. So the work done during this process, 1 to 3, is equal to 1271 kilojoules. Now you also wanted to show this process on a PV diagram or PNU diagram. So this is my pressure, this is specific volume. Let's say this is 100 kilopascal initially, this is 125 kilopascal during process, and let's say this is your phase envelope, right? During this process, initially you start at 100 kilopascal, right? The volume or specific volume does not change from state 1 to state 2 until you reach to that pressure. From state 2 to state 3, you are keeping the pressure constant because the piston starts to move. It's a frictionless piston, but your specific volume changes. Now finally you get to superheated vapor region based on our calculations. So that's it, and this is our diagram. All right, let me know if you have any questions.